There seems to be a profound gap in our understanding of the universe, one that could redefine modern cosmology. For years, scientists have wrestled with the core mystery: how fast is the universe expanding? This question has driven researchers to the edge of knowledge, where two conflicting sets of measurements have emerged. Observations of the present universe, which estimate the rate of expansion known as the Hubble constant, consistently show the universe expanding about 9% faster than predictions made using data from the early universe. For more than a decade, these two distinct types of calculations have been in conflict, leading to a growing puzzle that knows high hopes that the James Webb Space Telescope JWST, the most advanced and powerful telescope ever built, would finally solve the problem. This groundbreaking instrument, with its unprecedented sensitivity and clarity, was expected to provide definitive measurements to settle the debate. But to the surprise of many, the situation has only become more complicated. Rather than resolving the discrepancies, the telescope has revealed even more precise and detailed observations that highlight the inconsistency. Its data, rather than offering a resolution, has further entrenched the conflict. This brings the standard model of cosmology into question, suggesting that something fundamental in our understanding may be missing. There is now serious debate about whether new physics will be required to explain what is going on. The possibility that there is something we do not yet fully grasp about the universe is both astonishing and deeply intriguing. To better understand the stakes, we need to revisit the early history of the universe. The cosmos began with the Big Bang, an explosive event that saw energy, mass, and space burst into existence in an instant. In the first moments after the Big Bang, the universe was filled with a seething plasma, a hot, dense mix of matter and antimatter particles. These particles were created and then immediately annihilated each other in a cosmic struggle. Under normal circumstances, this matter-antimatter annihilation would have resulted in the total destruction of both, leaving behind a universe devoid of matter. However, scientists believe that some unknown process caused a tiny imbalance, allowing more matter than antimatter to exist. This mysterious anomaly saved the universe from implosion and enabled it to evolve into the vast and complex cosmos we observe today. As this primordial plasma cooled, gravity began to take hold, compressing pockets of matter. These pockets heated up, giving rise to sound waves that rippled across the universe, traveling at just over half the speed of light. These waves, known as baryon acoustic oscillations, played a crucial role in shaping the early universe. At the same time, the high energy density of the universe's packed contents stretched space-time, causing the cosmos to expand. Some of the matter from this period survived the extreme conditions, leading to the formation of the first structures in the universe. The standard story of cosmic evolution suggests that ordinary matter, which interacts with light, began to coalesce around invisible clusters of dark matter. These invisible structures formed the scaffolding for the first galaxies, which were interconnected by a vast, cosmic web that spanned the universe. As the universe continued to expand and cool, its energy density diminished, leading to a slower rate of expansion. However, around 5 billion years ago, this trend reversed. Galaxies began moving apart from one another at an accelerated rate, a phenomenon that scientists attribute to a strange and unseen force known as dark energy. Dark energy, which makes up roughly 70% of the universe's total energy density, remains one of the greatest mysteries in cosmology. The simplest explanation is that dark energy is a cosmological constant and intrinsic property of space itself that drives the accelerated expansion of the universe. This concept, originally proposed by Albert Einstein and known as lambda in his theory of general relativity, suggests that dark energy is woven into the very fabric of space-time, causing it to stretch. While the universe's matter density decreases over time as it expands, the density of dark energy remains constant. As a result, dark energy now exerts the dominant influence on the universe's expansion. The interplay between dark energy, ordinary matter, and dark matter forms the foundation of the lambda-cold dark matter lambda CDM model, the prevailing theory that explains the large-scale structure and evolution of the universe. According to this model, the universe's expansion rate, governed by these components, should be relatively well understood. Yet, recent observations have challenged this understanding. The lambda CDM model predicts a specific rate of expansion, but the conflicting results from different measurement techniques, known as the Hubble tension, suggest that something is amiss. One method of measuring the universe's expansion rate involves studying the cosmic microwave background CMB, the afterglow of the Big Bang. This faint radiation, emitted when the universe was only 380,000 years old, provides a snapshot of the universe in its infancy. The European Space Agency's Planck satellite mapped the CMB with incredible precision, allowing cosmologists to estimate the Hubble constant with less than 1% uncertainty. The results indicated a Hubble constant of about 67 kms per megaparsec. This means that for every megaparsec, roughly 3.26 million light-years of distance from Earth, a galaxy is moving away from us at 67 kilometers per second due to the expansion of the universe. However, another method of measuring the expansion rate relies on pulsating stars known as Cepheid variables. These stars, which expand and contract in a regular pattern, serve as standard candles that allow astronomers to measure distances across the universe. Henrietta Swan-Leavitt discovered in 1912 that the brightness of a Cepheid is directly related to the speed at which it pulses. By measuring the brightness of these stars, astronomers can determine their distance and use this information to calculate the expansion rate of the universe. Using Cepheid variables, along with other standard candles like type Iowa supernovae, Nobel laureate Adam Rees and his team have calculated a much higher Hubble constant of about 73 kms per megaparsec. This result is significantly faster than the rate predicted by the CMB data, creating a significant discrepancy. The Hubble tension has only grown more pronounced as more precise measurements have been made, including recent observations from the James Webb Space Telescope. Instead of resolving the issue, these new observations have reinforced the conflict, leaving cosmologists grappling with the possibility that new physics may be required to explain the expansion of the universe. The debate over the Hubble tension has divided cosmology into competing camps. Some argue that the discrepancies arise from measurement errors, while others believe that the standard cosmological model itself is flawed. There is also the possibility that dark energy behaves differently now than it did in the early universe. If dark energy was stronger in the past and has since weakened, it could explain why the expansion rate appears slower when we look back in time. Alternatively, some theorists propose that there may be two different kinds of dark energy, or that dark matter interacts with light in unexpected ways. The mysteries of dark matter and dark energy are not the only puzzles that the James Webb Space Telescope is helping to solve. When the telescope was launched in December 2021, it was tasked with looking further back in time than any previous instrument. Its advanced infrared capabilities allow it to peer deeper into space, capturing light from galaxies that formed just 300 million years after the Big Bang. These early-stage galaxies were expected to be simple, filled with hot, young stars forming at a rapid pace. Instead, Webb's observations have revealed that many of these galaxies are far more massive and developed than predicted, containing heavy elements from earlier generations of stars, and even hosting supermassive black holes at their centers. This surprising discovery challenges our understanding of how galaxies form and evolve. The early universe was supposed to be a time of rapid star formation, but the presence of complex, mature galaxies so soon after the Big Bang suggests that galaxy formation may have been more efficient than previously thought. This raises important questions about the processes that shaped the universe in its infancy and hints that our current theories may need to be revised. As James Webb continues to provide unprecedented insights into the cosmos, it has also deepened the mystery surrounding the Hubble tension and the nature of dark energy and dark matter. These elusive components, which make up the majority of the universe's content, remain poorly understood. Solving these mysteries may require not only new data but also novel theoretical frameworks that go beyond the current models of physics. Cosmologists are exploring a wide range of possibilities, from modified gravity theories to exotic particles, in the hope of finding answers. In conclusion, the discoveries made by the James Webb Space Telescope are revolutionizing our understanding of the universe. Its ability to probe deeper into space and time than ever before is revealing new complexities about galaxy formation, dark matter, and dark energy. As we continue to explore these frontiers, the telescope's findings are reshaping our view of cosmology and may ultimately lead to groundbreaking discoveries that challenge our understanding of the fundamental nature of the universe. The pursuit of these answers is one of the most exciting endeavors in modern science, and the secrets of the cosmos await as we push the boundaries of knowledge further than ever before.